Well, as you might suspect, you'll have expansion in area and volume. See, as you see, when we were dealing with linear expansion, we were only looking at the expansion along one direction. But if you were to look at, say, a rectangular plate with dimensions L0 and width 0, we would find that the initial area will expand both in width and in length. So the change in area, for example, would be the original area multiplied by twice the linear coefficient of expansion times the change in temperature. What you could do is, I suppose, is to find the change in width and change in length and multiply the new width and length to find the new area. So that's one way to calculate, say, the fractional change of that area would be really just 2 times the coefficient of linear expansion times the change in temperature. And similarly, we know that the same thing would happen with volume. So the change in volume would be equal to, that fractional change would be equal to 3 times the linear coefficient of expansion times the change in temperature. Think of it as 3 dimensions. When we replace this typically with a value of beta times delta t, and typically beta is approximately 3 times alpha, the coefficient of linear expansion. Since liquids do not necessarily retain the same shape as they expand, the quantity is uniquely defined as the change in volume, and hence we have a table of values for these beta values. And they could be found in your textbook for common liquids and gases. The cavity that holds different solids, you have to think, can expand as well. So if you take a look at example number 4, we have a glass flask. So imagine you have this glass flask, okay, like a beaker, that has a volume of 200 centimeters cubed. And we see that it's filled with mercury right to the brim. So as you heat both the glass and the mercury from a temperature of 20 Celsius to 100 Celsius, so this is our initial volume, our change in temperature is 80 degrees Celsius, or you could say 80 Kelvin, because that would be the same incremental change. We'll find that they both expand. However, if you look carefully, the coefficient of expansion for glass is only 1.2 times 10 to the power of negative 5 Kelvin to the power of negative 1, while the coefficient of mercury is actually 18 times 10 to the power of negative 5 for Kelvin to the power of negative 1. So what we'll see is that this glass container will expand outwards. Remember, it's not going to expand inwards because it's going to get larger in size. But the glass is not expanding at a quick enough rate compared to the mercury. If these were both the same, then they would be exactly still filled to the brim. But because mercury expands at a greater rate than glass, it's going to overflow. So yes is the answer to that. Yeah, it's going to overflow. How much does it overflow by? Let's calculate that now. Okay, what we're going to do is we're going to find out how much does the glass expand by. So the change in volume of the glass will be calculated by using the initial volume of 200 centimeters cubed multiplied by the volume expansion for glass multiplied by the change in temperature. So this is going to give you 200 centimeters cubed multiplied by 1.2 times 10 to the power negative 5 and Kelvin to the power negative 1, and the change in temperature is 80 Kelvin. That means it only gets an extra volume of 0.192 centimeters cubed. Now let's compare that to the change in volume of the mercury, which would be the same initial volume, but different coefficient of volume expansion, but the same temperature change. So we have 200 centimeters cubed multiplied by 18 to the power of negative 5 and kelvins to the power of negative 1, and then a change in temperature of 80 Kelvin. So that gives you a change in volume of 2.88 centimeters cubed. So it will overflow by the difference between these two volumes. So the volume expands, of the glass expands by 0.192 minus the change in volume of the mercury. And it appears I have a small error, 2.88 centimeters cubed minus 0.192 centimeters cubed will give you an answer of 2.688 centimeters cubed, which is 2.7 centimeters cubed. And it looks like I forgot to put a little decimal place right there. Okay, and that's it for example number 4 in our discussion of volume expansion.